Hello everyone. This is part 4 of section 14.6 Directional Derivatives. Last time we saw a couple examples of finding the gradients, and then we looked at level curves, and finally we left off with defining the maximum increase and maximum decrease of a function at a point. So that was just the gradient, magnitude of the gradient is the maximum increase. Think of that as the steepest slope. And so we'll look at some examples and finish off this section on the next page. Sorry about the delay. Okay, so we want to find a unit vector in the direction in which this function increases most rapidly at that given point, and also find the rate of change of the function, which basically means how fast is it, what is its maximum increase. So recall the formula for the gradient, which will give us the vector where the maximum increase is, and that is, without using functional notation, I'll just say f of sub x times I plus f sub y times j, which of course means partial of f with respect to x times I plus the partial of y with respect to times j. And so we'll find the partials. So x squared, partial with respect to x, derivative of x squared, 2x. Y squared basically differentiates to be 0 because it's a constant. Similarly, partial with respect to y is going to be 2y. Derivative of x squared is a constant. You could do this in one of two ways. I suppose what you could actually do is write the vector, or write the gradient as a vector that is a function. That is, f sub x is 2x times I, and then plus f sub y is 2y times j. And then you could actually just plug the point 1, 2 in there, and that would give you the vector for maximum increase. But if you want, I've been doing this where I've shown the substitution into the partials, and then substituting into the definition for the gradient. So f of 1, 2 would be 2 times 1, or 2, for the partial with respect to y at the point 1, 2. Be 2 times y is 2, or 4. So therefore the gradient of f at the point 1, 2 is going to be f sub x, or 2 times I, plus f sub y, which is 4 times j. And if we want the unit vector, it's basically, you don't have to really write out a formula for it, but if you wanted to, it is the gradient of f divided by, because that's going to be a vector, divided by its magnitude. So in our case, 2i plus 4j divided by its magnitude, which is the square root of the sum of the squares. So the square root of 2 squared plus 4 squared. So we have 2i plus 4j over the square root of 20. And so we get 2 over the square root of 20 times I plus 4 over square root of 20 times j. And you could simplify the radicals, make them look a lot prettier, but I'm not actually concerned about that. So that's the unit vector in the direction where the function increases most rapidly And then the maximum increase is really just the denominator of that. It's really just the magnitude of f, which is the square root of the sum of the squares again. 2 squared plus 4 squared, or the square root of 20. Okay, so one more example similar to that, and then we'll wrap it up with a quick summary of some other things that we've already done. But here, just an extension to a function of 3 variables. So essentially same idea in terms of the formula. The gradient of f of x, y, z now is f sub xi plus f sub yj plus f sub z k. So find the partials. F sub x would be, okay, with respect to x, 3x squared, z squared times long, and the derivative of the rest is 0 because there's no other x's. The y's and z's are held as constants, of course. For the y, no y's here, so its derivative is 0. Here we get 3y squared times z. And then the derivative of these terms are 0. And then finally, the partial with respect to z. Excuse me. Okay, here we get 2z times the x cubed, so 2x cubed z. Here we get the derivative of z is 1, so plus y cubed, and then the derivative of this z is 1, so plus 1, and the derivative of the constant, of course, is 0. So now, again, I'm just going to evaluate each of these. If you want to modify the notation and you don't feel like showing this the way I'm showing it, that's fine as well. But this shows us we're evaluating f sub x at the point 1, 1, negative 1. So that's 3 times 1 squared times negative 1 squared. And so that would be positive 3 for f sub y at the point 1, 1, negative 1. That's 3 times 1 squared times negative 1. So that's negative 3. And f sub z at the point 1, 1, negative 1 is 2 times 1 cubed times negative 1 plus the negative 1 cubed and then plus 1. So it looks like we get a negative 2 minus 1 and plus 1. So negative 2, oh, I'm sorry, here's my mistake. This should be a positive 1. Sorry about that. The 1 that's being cubed is the value of y. So I'm glad I caught that. That's a positive 1. And that gives us 0. Okay, good. So now the gradient is defined, well, we defined it up here. So we'll say the gradient at the point 1, 1, negative 1 is now f sub x at that point, 3 times I, plus f sub y at that point, negative 3 times j, plus f sub z at that point, 0 times k. So just 3i minus 3j. Okay, so then if we want the unit vector, the formula for it, it's just that gradient, or just say u is equal to that gradient as a vector divided by its magnitude. So 3 squared plus negative 3 squared. So we get 3i minus 3j over the magnitude is the square root of 18. And I'm just going to leave it as 3 square roots of 18, 3 over the square root of 18 times I, and then minus 3 over the square root of 18 times j. And if you wanted to, you could simplify that and it'll make it look a lot prettier. But I'm going to leave it at that and go for the maximum increase, which really we already found. It's the denominator here, the magnitude of our gradient. So the square root of, again, 3 squared plus a negative 3 squared, which is the square root of 18. Okay, so that's pretty much it for the section, but I wanted to look at some extra practice and notice how we've been using the i's and j's a lot, and this is our vector notation. So recall that AI plus, notationally, A plus BI, and using our vector form, is AB in these triangular brackets. So this is, I'm sorry, I should say AI plus BJ, or so AI plus BJ. I was chuckling because I was thinking about complex numbers. We're studying differential equations. So AI plus BJ is given as in vector form as AB. So here we want to find the directional derivative, and recall the formula for the directional derivative was, put it over here, that the directional derivative in the direction of u of the function f at a point x sub 0, y sub 0 is equal to the gradient at that point dotted with the unit vector. So the first thing to note is that this is a vector, and it is a unit vector. So therefore, if we just dot the gradient with that, and it's a unit vector because if you take the magnitude, it's 1. If we dot the gradient with that, that's going to be our directional derivative, which we interpret, of course, as our, as our slope. So we'll find some partials. Partial of f with respect to x would be 4x, and then plus 3y, because y is a constant, or to 3x is 3. So there's the partial with respect to x, partial with respect to y. Okay, x is held as a constant, so here the derivative of 2x squared is 0, and the derivative of 3xy, since x is a constant, derivative of y is 1, so we just get 3x. Okay, and then if we evaluate those at the point 1, 3, f sub x at 1, 3 is 4 times 1 plus 3 times 3, or 13, and f sub y at the point 1, 3 is going to be, okay, f sub y is 3x, so 3 times 1, or 3. Okay, so I'm just double checking here. Yeah, 3x and x is 1. Okay, so we're good. So therefore, the gradient then at the point 1, 3 is going to be equal to 13i plus 3j. And I'm going to choose to put that into the vector form, 13, 3. And our directional derivative then at that point is the gradient 13, 3 dotted with the unit vector, and the unit vector was 1, 0. So 13 plus 0, or 13. Okay, so the problem with this one is we're going to pretty much do the same thing, but we're first going to find out what the unit vector is. So the unit vector, recall, is the given vector over its magnitude. So I'll say 2, 3. I'll use the vector notation because it makes it a little bit easier. So 2, 3 over square root of, looks like 4 plus 9, 13. So we get 2 over the square root of 13, 3 over the square root of 13. That's our unit vector. So therefore, our directional derivative at the point 2, 3 is going to be given by the gradient. Okay, the gradient we had already found, that's up here, so that's why we didn't have to find it again. That was the gradient. So we take that again, 13, 3, now dotted with 2 over the square root of 13 and 3 over the square root of 13, and we get 26 over the square root of 13 plus 9 over the square root of 13, or 35 over the square root of 13. Okay, so then what makes this one different is because we're headed toward, we want the directional derivative, but headed toward this point. So I'm going to call the initial point, the given point that we've been working with, p sub 0, and that is the 1, 3. Oops, guess I just noticed I made a mistake here. This was the directional derivative of f at the point 1, 3. Okay, so back to this one. I'll call the initial point 1, 3, and then the point that we're headed toward I'll call 2, 5. And then we have to find its unit vector. So first find the vector itself. P sub 0 to P1 would be 2 minus 1, so I'm going to use vector notation again for simplicity. 2 minus 1, 1, 5 minus 3, 2. And so then the unit vector is going to be that over its magnitude. So square root of 1 squared plus 2 squared. So we get 1, 2 over square root of 5. So the unit vector 1 over square root of 5, 2 over square root of 5. So then the directional derivative at the point 1, 3, headed toward this this point would be this unit vector. So we take the gradient, again 13, 3, dotted with 1 over square root of 5, 2 over square root of 5 vector. And that gives us 13 over the square root of 5 plus 6 over the square root of 5, or 19 over the square root of 5. Okay, and then finally, the last question is theta is 30 degrees. So we have a little sketch here. Excuse me. We'll have a 30-degree angle. Let's call that our unit vector. So then dropping a perpendicular, that would be the U1 component in the x direction, and the U2 component in the y direction. And if it's our 30, 60, 90, opposite 31, hypotenuse 2, opposite 60, radical 3. So U1 is going to be the cosine of 30 degrees. So that's adjacent over hypotenuse, so radical 3 over 2. U2 is going to be the sine of 30 degrees. So opposite over hypotenuse, or 1/2. And then our unit vector can be expressed as square root of 3, 2, and 1/2. Again, we'll use vector notation. Okay, so then finally, the directional derivative in the direction of that unit vector of the function at the point 1, 3 is the dot product of the gradient, 13 and 3 that we've been using, times this unit vector, 3 over radical 2 and 1/2. So that gives 13 radical 3 over 2 plus 3/2. And I guess that's about all you could do. I suppose you can make it a single fraction. 13 radical 3 plus 3 over 2. But you can't really do much more than that. Okay, so finally that ends section 14.6. So when you're ready, come back and we'll be looking at section 14.7.